Yeah, so this week we will we'll talk about the FramePack paper, which is from the legendary Levin, who invented ControlNet, IC Lights, and a lot of amazing works in computer graphics and vision. So this is his latest work. It's called FramePack, and what it does is that it, unlike traditional video generation model, that they have to rely on context, a long context length. FramePack try to compress the input frames to make the transformer context a fixed number regardless the video length. So that in the first maybe we can read the abstract together. So we'll have a brief overview of what the paper is about. So here they basically say that they present a neural network architecture FramePack, and then they said they compress the input frames to make the transformer context length a fixed number regardless of the video length. And as a result, so this is like one of the selling point of the paper. Like it will be able to process a large number of frames using a video diffusion with computational bottleneck similar to image diffusion. So so the compression um makes it an advantage. And then because the compression works, so that also means when they want to train the video model, they can use a significant higher batch size because now it's using less memory, right? And and then they try to mention there is a anti-drifting sampling method that can generate frames in an inverted temporal order. We don't know what it means yet, but probably something new. So we will figure this out later. And then they said, oh, finally, we show that existing video diffusion models can be fine-tuned with FramePack. And they claim that the visual quality may be improved because the next frame prediction supports more balanced diffusion scheduler. So from what I know is that FramePack has become vital because it supports popular video diffusion models like Hongyuan video and also WAN 2.1, which are the popular models that the open source community use nowadays. So now I'm highlighting those paragraphs or keywords. Like I personally like to use yellow for the gimmicks or the motivation, and then I use blue for some keywords that might be useful, and mainly the red underline for the insights. So first, let's read the introduction together. I think this paper it writes pretty well. So first of all, in the introduction, it just go straightforward to make the definition like what is forgetting and drifting, and it just said, okay, forgetting refers to the fading of memory as the model struggles to remember the earlier content. So that means, let's say you have a video, and then when it goes over time, it does not know what it previously generated. So that leading into the temporal inconsistency, right? So that means like the problem is from the semantics, and then there is drifting, which refers to the iterative degradation of the visual quality. So the keyword here is the visual quality due to the error accumulation over time. So this one is related to perceptual. And then the whole paragraph below that is that after the definition, they try to state their motivation of what they want to do. So in the past, like people in the previous work, they have been trying to mitigate the forgetting problem by enhancing memory that also may also make the error accumulation faster. And then that also makes drifting. But other people, they are trying to reduce drifting by interrupting the error propagation, and that in that case, that harms the another one. So it's more like a trade-off. And they also talk about like what's the naive solution to tackle this kind of stuff. So for the forgetting problem, like a naive solution is to encode more frames. So if the model forget what it previously was generating, then we can just give it a longer context window, right? Like encode more frames. But it becomes computationally intractable, right? Because the complexity of transformer can go up to very large. And I think the author pointed out a very interesting properties that the video frames contain significant temporal redundancy. So let's say you have a video and then in between the frames, there will be a lot of things that can be overlapped, right? So that's why when people are compressing the video, let's say the MP4 format, like in fact, we compress a lot of image using the temporal redundancy there so that we get the MP4 compression format. So this paragraph is mainly talk about the author wants to come up a effective compression system to tackle this forgetting problem. So it's more like a motivation. It hasn't discussed what to do yet. And then it talks about the drifting system, like a drifting problem. So the drifting problem, uh, the authors also mentioned, okay, what previous work did. And what it claims is that a stronger memorizing mechanism also memorize more errors and thus accelerates the error propagation when errors do occur. So that means if you're encoding more frames to have a longer context, then it can, if there is some error inside, then as you're memorizing more and more frames, then there could be more and more errors, right? And this accelerates the error propagation. So that's why there will be like a trade-off, and we need a carefully designed sampling method to do the error correction. So here's the motivation part, and that jumps to what they are doing. In this paper, we propose FramePack as an anti-forgetting memory structure. So FramePack is the solution for tackling the forgetting problem. And with anti-drifting sampling method. So they basically propose a sampling method to target this drifting problem. So the FramePack does is that they're compressing the input frames based on the relative importance, ensuring the total transformer context length will cover a fixed upper bound. There's a fixed upper bound, regardless the video duration. So it didn't say how it's done. It's more like a trailer. It's more like a trailer of okay, we propose something and then yeah, it works. And then there's also say okay, we propose the anti-drifting sampling methods that break the causal prediction chain by incorporating the bidirectional context. So now we know this sampling method is related to bidirectional. And they say that okay, generating endpoint frames before filling the intermediate content, and an inverted temporal sampling approach where frames are generated in the reverse order, each attempting to approach a known quality high frame. So it's more like a input frame in image to video task. And they said that okay, the methods improves. And then in the last paragraph of the introduction is always gonna be when you try to reclaim your contribution, I think this is relatively concise to write. It's basically, to sum up, they said we propose a lightweight method that can be built on top of the video diffusion models. It's basically like a fine-tuning method, and then it improves the quality of the video, and furthermore solving the forgetting problem and also the drifting problem. So we can skip the related work for the moment, and let's jump to the method. So the author said we consider a video generation model that predicts next frame repeatedly to form a video. For simplicity, we consider a diffusion-based next frame prediction model using diffusion transformers so that they can generate a section of S unknown frames. So let's put this as an unknown frame. That is conditioned on T input frames F. So those squares are the known frames. And in here, all the frames and pixels, they refer to latent representations because DIT, and most of the modern video generation model, we first use a VAE to compress those video pixels into latents so that we can, so it's more like another layer of compression. And then, okay, they said, okay, for next frame prediction, S is typically 1. So it's more like an iterative next frame prediction, keep predicting the future frame. And they focus on challenging cases where T, which means the input frames, are much higher than the output frames. And they claim that because like for a 480p frame is around 1.5K tokens. It's about 1.5 tokens. So basically, if you want to generate a video using the model, then your total context length will be L equals to LF, which is the context window of one frame, context length of one frame, and then multiplied by your input frames plus the output frames. And this will cause the content length explosion when the T is large. So now the problem is getting obvious. And then now we talk about FramePack. So the observation is that they see the input frames have different importance when predicting the next frame. And we can actually assign an importance to the input frames. And I think we can just think, okay, let's say you want to generate the next frame, then it's gonna be obvious that the most important frame are gonna be the previous frame, right? Let's say you want to generate T, the T plus 1, and there are some like multiple frames before it, then this one is gonna be highly correlated with this one, right? So it used this idea to say that frames temporarily closer to the prediction target can be more relevant. So that's why they said, okay, the F0, which is the current frame, are being the most important, and the oldest one, let's say this is like a T minus 1, are the least important. And they said we define a length function phi f that determines each frame's context length after the VAE encoding and transformer patch defining, which I previously just explained it. This is how we get the context length after the VAE encoding and the transformer patching. And applying this progressive compression to less important frames as this equation, which basically, let's say you have a frame like F0, F1, F2, F3, which the video plays in this direction, and you want to generate like a new frame. Then in the input context, the most recent one is the most important, right? And that it just assume that maybe the frame before the most recent frame like half, like that. So there's a compression ratio, and then let's just assume it 2 here, so that if 8 will become 4, and then the next frame will become 2, become 1, blah blah blah. So there will be a compression ratio, and this will form something. Okay. Okay, I didn't see the. Yeah, so it will form something like this, where the most recent frames share the largest portion, and then the more older frames, they will have a less they will have a less semantic meanings encoded. So with this equation, the authors found that when you're trying to add up all the t values, it will follow a geometric progression. So that this is like a geometric multiply to infinity problem, and the total length will converge to this equation. Which surprisingly, you will see now, it does not depends on the input frames anymore. Like previously, we discussed that the input frames are the t values, right? Conditioned on t input frames, and then the context length is computed by LF times t plus s. But now the new context length, the t is gone, so that we only care about the generated output frames. Because in t, it can be compressed to a fixed number. So now it just becomes irrelevant. So there's like one core findings in this paper. And then they also discussed that, okay, actually we can besides this kind of simple ways to compress, they also find other different relevance way to do this. So let's say what it says that we can basically represent arbitrary compression rates by duplicating or dropping several specific terms in the power of 2 sequence. So let's say if you don't want to do it in the 2 scale, you can actually add some term inside. So let's say you have like a 1 and then 0.5 and then plus another 0.5 and then 0.25 and then 0.125, 0.125 again. So following this, it can convert any rate value. So basically you can want any compression you want, just depends on how you want to compress this. So in this here is basically duplicating some frames with the same compression rate. So that means, okay, you think maybe in this situation, the previous 4 frames are equally important, then you just assign them with equally importance frame. And in actual implementation, when they're doing this, they use a 3D kernel to downsample to downsample to downsample the frames as the compression. So that's why what they're saying is that in this petrify operation is basically you can do it in any way you want as long as it can mesh the dimensions. And then now there's a problem. So let's say when you're having like a compression and then it becomes small, it becomes so small. Then what about this? Like eventually you have a lot of tails, right? And when the input frames length are extremely large, in the tail area, the frame may fall below a minimum unit size, let's say like single unit, like a single latent pixel. So the author discussed three ways to handle the tail. Maybe we can simply deleting those, or we can do some average global pooling, or we can allow it to allow the text tail frames to increase the context length. So I think this is a straightforward way to think of it. But the authors think in their test there are no visual differences. So I think we can just dump the tail frames, because when you compress this to so small,
Hey, Max, are you leaving?
Yeah, I,
Ah,
I think he disconnected. So
yeah,
yeah, let's wait for him.
yeah.
hello.
Hello.
Uh,
Yes.
it seems I accidentally quit the app. Where were we?
Yeah, I think you're
Uh,
explaining chopping the tail.
Is it? Oh, is it still recording? Okay, it's still recording.
Yeah, it's still recording, I guess. Yeah, yeah.
Yeah, so we can simply delete the tails, and then the author also added that when encoding the inputs with different compression channels, because it requires the ROP alignment, which is the position embedding for the time steps. So they simply do a average pooling to to kind of force them match the compression kernel. I think here this is not it's just a minor stuff. And then now they discuss the FramePack violence. So they visualize the typical structures, saying that uh, so here this one is the structure that we just discussed. That is like A's to 4, 4 to 2, 2 to 1. And there can also be progression with the case level. Let's say you can have multiple frames sharing the same compression rates. And what more interesting is that you can actually patch multiple frames to in one tensor, so that they can share the equal the equal length, like he mentioned here. Like compression can be also applied in the temporal dimension. This method encodes multiple frames in the same tensor, which is naturally aligned with the DIT structures. And like why is this important? Because it really depends on your use case. So let's say if you're doing like image to video generation, your initial frame usually care like a higher importance, right? Then maybe this kind of like frame 0 having a sorry, maybe this like progression with an important start, like this kind of last frame and first frame having the most important start would sorry. So let me put it this way. So T1, so a video play in this way, and then you have a video go like this, and here is ft minus 1, which is the starting image. And then you have the last image, which last image is f0. Then you want to predict the f minus 1, which we don't know, but because we are doing like an image to video problem, so that's why in this kind of compression rates, it would be very beneficial for the I2E problem.
Could you explain again what this petrifying kernel means? Like there's like a top of 122, 144.
Oh, so the petrified kernel is that when so in typical modern video models, you have to go through a VAE, and then after the VAE, because it goes into a diffusion transformer structure, so you need to petrify the compressed latents into tokens.
Mm-hmm.
So this go through the petrified process.
From
And
latent space to token.
yes.
And what does the number like the 122 or 144 mean?
So 122 is basically like the kernel, how the kernel is specified. So the first is the frame, and then the second is the width, and third is the weight.
Oh, I
First
see.
with the height,
Okay.
if I remember it correctly, it should be yeah, I think it's written somewhere. Oh, here, yeah, right. The 3D kernel as the PF, PH, and PW, representing the steps in frame number, height, and width. Yeah,
Okay, thanks.
so it's basically on how you design the kernels.
I see. Thanks.
And then yeah, like previously I just discussed like why this become interesting, because it can be very beneficial for important tasks such as the input like a image to video task. And then now it talks about a drifting problem. So this one is just useless. Like it's just kind of remind you that drifting is a problem, that the visual quality degrades as the video length increases. So it's more like a perceptual issue. So the author also doesn't know like what's the underlying cause below that. But what they observe is that this drifting only happens in causal sampling, which means so let's say you have the frames going toward, and then for each next frames it depends on the previous frames. So there's a causal relationship, and then the model can only access to the past frames. So we show that what if we also get access to future frames? So this will be like a traditional way, and this will be let's say I added like a future frame here. and then when I draw the frame, it will attend to both frames in the bidirectional way.
Oh, wait, can I ask a question? Like, is the input right now an image or like a video, so that you
Yeah,
can have a future frames
input is a image.
in image? Then why there is future frames that the model can the current frame can have access to?
Oh, you mean this one?
Like it says that providing access to future frames, but my question is like, where do those future frames come from? Do they get generated before?
Yeah, it can be generated. It can be
Okay.
generated, and also you can, if you want, you can also inject your own image into it. So it can be generated, or it can be also,
But
like an image input.
I see. But if it's generated, maybe this type of drifting, because drifting is caused by error accumulation,
Mhm.
and it's like the causal relationship, right? And
Yeah.
if the future frames are also generated, then that errors will also be propagated, right?
Not really, because when you like what we said, what we previously discussed is that when we generate the traditional model, like which the traditional image generation, sorry, the traditional frames generation, it depends on the previous frame, right? But what
Yep.
if we want to first generate the last frame? Like we generate
Oh,
the last frame, yeah. So
it's like a
later,
backwards.
yeah,
Mhm.
later we will discuss how it was done.
I see. Okay, thanks. Yeah, I think we talk about like bidirectional. That maybe that's why, or what bidirectional means, right?
Yeah.
Okay, thanks.
So so there is a vanilla sampling method that's iteratively predicting the future frames. It can actually be modified into figure 2b, where the figure 2b is here. So usually it will be having like a t minus 1, and then it's really like this: f0, f1, f2, f3, da da da. So this is like the traditional method, how it was done, like what I just drawn. And the author proposed you can actually do like an anti-drifting. So at the first time step, when we're generating the frames, not only generating the first frame, but we also generating the output, like the future frame. Then in the intermediate latents, then we just simply go the normal way, so that when we generating the intermediate latents, it will attend to both the future and the input. So yeah, he also mentioned that like where the first iteration simultaneously generating both beginning and ending sections, while the subsequent iterations fill the gaps between these anchors. This bidirectional approach prevents drifting, since the ending frame are established in the first iteration. But there's another important variance that they invert the sampling order into figure 2c. So instead of doing this, they simply doing this way, while we also generating like the last frame and the first frame at first, and then we generating from the backwards. So they discussed this, and they said this approach is highly effective in image to video generation because it can treat the user input as a high quality first frame and continuously refines generation to approximate the user frame. So this can lead to a high quality videos. So I think here is like one of the highlights of the paper. And they also mentioned that, like, interestingly, the free methods, because we are using FramePack now, so theoretically, all the sampling methods, even the vanilla generation method, can generate videos in arbitrary length. So that I think in the demo they actually show that they can generate up to 1 minute video. Oh yeah, they also, like here, they also mentioned that, like, in practice it can generate 1 minute. And they also mentioned that to align the ROP with random access, they simply skip the non-query phase in the time dimension. So here is how the paper works. And there are some experiments, like I think it's a bit messy here. And what it's basically saying is that they try to show that the inverted sampling method perform the best in both human. So you can see here, it's going the best. And then it's also performing pretty good in the global metrics, which this global metrics actually comes from the WeBench paper, which is another video benchmarking work. And those are all automated evaluators. So they said basically, if for one section you can generate 9 frames, and then they found that this will be the best solution. And also you can use the inverted and anti-drafting sampling. Will be the best combination of it. So about how the model is trained. So they already did 2 implementation with Huan and Hongyuan video. And basically they did some modification with the architecture. I think here maybe, like, I didn't dig deep in this part, but I think it might not be very relevant. But I think what is impressive is that because with FramePack, they can actually use a higher batch size to train the model. That means you can use fewer resources. And what they say is that they recommend Hunyuan video as the configuration. And when they do the training, they use the LTX video, which is another video model, the dataset collection pipeline, so that they basically collect video in multiple resolutions and quality levels. And then they just filter the bad one using the motion scores. I think this motion scores are probably some motion, flow, sorry, what is it called? Motion predictors. Yeah, optical flow motion predictors. I think it's probably something like this, so that they can make sure it has a diverse distribution. So it's basically, okay, it has some buckets here. And then they use like a Ada vector optimizer, which I think it shouldn't have much it shouldn't have much large impact, but I think most of the contribution come from the FramePack architecture. And when they want to evaluate this, they do a small scale human study. So there will be like 500 prompts for text to video and 500 for I2V task. And then they use the 30 seconds long video and 5 seconds for short video. So they also do it for 2 types of tasks, like long and short. Then I think this are pretty truthful because they came from the rebench metrics. But basically, they have different dimensions in measuring different stuff, like the aesthetic Lion predictor, which is pretty trivial. And I think surprisingly, we can see that in the dynamics. I think the paper discussed something regarding dynamics, but I just forgot about this. But I think it's not really important. I think the authors they just conclude that the inverted sampling is the best, although their dynamic score isn't the best. But that is because I forgot what's their assumption here, but it's probably not so important. Yeah, so that's pretty much the paper. Because now we only have 10 minutes left, so maybe I will stop here and then maybe we can do some discussion.
Thanks for Max. Good to present this paper, but I'm curious about and not quite get that why inverted anti-drifting will be better. It's just it's just an empirical result, or do they have any insight or something can tell someone else to know that sorry, invert anti-drifting will be better, sampling will be why it will be better. Yeah.
I think what it meant because when you do the yeah, I'm also thinking about it because in the paper I think this thing is this part like adding the last frame. I mean adding future frames at the first iteration is probably the thing that makes the thing work. But
yeah,
I like so
Yeah, I
so
mean,
because
Yeah, maybe
sorry.
let me get the. I'm sorry. So
yeah, go
you
ahead,
wanna
go
say?
ahead.
Okay.
Yeah, so maybe let me give a word here. I'm just guessing the reason. Yeah, in terms of math actually, because when you are doing the diffusion transformer, you're actually doing many conditional probability thing, and actually you're doing optimization, but you condition on something, all right, and do it probabilistically. So now in terms of like the Bayesian point of view. So now if you do that like invertedly, so it may help you to get something better off during the optimization. So maybe let me explain it in a more concrete way. Yeah, so it would be more like if you if you are trying to like Yeah, so okay, so it's like this. So now you are like multiplying two numbers, all right? And those two numbers are not exact numbers. They are
Mm-hmm.
basically like irrational. So they're pretty random. Those decimal places are pretty random. So if you're using like computer to do that, you cannot like this computer is discrete, right? So it
Yeah.
cannot like really store all the decimal places. It's basically doing like discretization every step, right? So
Mm-hmm.
every time so now all right, now you do that multiplications like one time, like you have two numbers, you do that one time, and now you get a product of that. All right, that's step one. And now you multiply another number to it, and that number is also not exact. Every time when you do that, you're actually accumulating some error, right?
Mm-hmm.
Right? Yeah.
Right. Yeah.
So now the inverted way is like, well, so you guess the product would actually be an somewhat a nice number, an exact number, all right?
Mm-hmm.
And now you do it invertly, and you do it invertly in the way like, well, so you just factorize that nice number into two not too bad number, and then and those two not too bad number, you further factorize it into like four not too bad number, and then finally you try to approximate the whole way like invertly. Yeah, so that you avoid in the beginning, if you do it in a direct way, you will accumulate the rounding error. Yeah, so this is just the analog. It's not exactly what it's doing, but I'm guessing the principle is like that.
Yeah.
Yeah, I think generally, like if you already know the outcome, it would be easier to deduce what happened uh beforehand, rather than like you just uh uh inferencing things in the forward, where at the end you get the results.
Mm-hmm.
Yeah.
Yeah, I think it also has something to do with the temporal relationship, right? Because he's trying to solve this like a trade-off, like you need to strike a balance between how you wanna depend or condition your current frame on the past frames. And I think the author is just trying to maybe to some extent trying to reduce the degree that it kind of condition on the past frames. And I think it might make sense if we try to look at from this point of view that let's say put into an analog, like if somebody is trying to ask you, like your boss, your professor is trying to uh, ask you to achieve something, and you can actually, if you can make a plan first, maybe for your the following week, and then you kind of starting from the goal, and then you build up step by step from the goal backwards to your current progress. I think it will kind of also prevent you from deviating, or drifting to a random place. I think maybe if you try to look at from this angle, it kind of makes sense as well.
Yeah. We can look at what the author said. Continuously refines generation to approximate the user frame. Yeah, actually, I don't really understand what he's saying here. Effective for image to video generation because it can treat the user input as high quality first frame.
Yeah, I think this part the author is not writing very well because he didn't give any kind of insight. Yeah, so yeah, but I can understand. I think and um the base you say the baseline perspective and the planning perspective. Yeah,
Yeah, because this is not the conference version yet. I think this probably will appear in new rips.
yeah. Yeah, something like that. Because I think the main idea of the split the packed frame is very simple. So I think they try to get our archive up ASAP. Yeah, so could have still have some issue to fix.
Yeah, so I actually did play with the model, and I think it works extremely well in mm, in the human dancing kind of stuff. I think you can go to the GitHub page. Let me stop